Okay, hi guys. So in this lecture, we'll be seeing some more examples on Hoffmann Bromamide reaction, and we'll again see the mechanism by a separate example. Okay. So let's say we have this compound, wherein we have this amide, okay, and we have again Br2 in presence of as a basic medium. So we have KOH here. Okay. So it will convert into again PHNH2 plus obviously KBr plus either you can evolve CO2 gas or you can make K2Cr K2CO3. Okay, both are the same thing. Okay, so what will happen in the first step? So how many moles it would be needing, how many moles of KOH it would be needing, that would be determining in this example, and it should be come out to be answer as 4. Okay, so let us see the mechanism. So we have in the first step we have obviously we have the amide part, and on amide OH minus is getting the H plus from the nitrogen atom, resulting into the formation of N minus H. Okay, so this N minus H will go and attack on Br. As a result, we will get something like NHBr. Okay, in the next step what will happen is again OH minus will again be attacking on, or rather OH minus will be rather attacking on the hydrogen atom, on the nitrogen group or nitrogen atom, and will be getting something like N minus H, or rather N minus Br. Okay, so next what will be happening? So this is the RDS step. So in the RDS what will happen is it will form a double bond here. Br minus will be leaving. As a result, migratory aptitude will be shown by the pH group, and we'll get something like this. Okay, this is isocyanate. Okay, this is isocyanate. Okay, next what will happen is on this isocyanate again one OH minus will attack on the carbon atom. Okay, and as a result we will be getting something like C double bond O, OH here, and we'll be getting again negative charge would be coming on nitrogen atom, and pH would be there. Okay, next what will happen is again the N minus will take one hydrogen atom from the water molecule, and at the same time okay, I'll write in the separate step NHPH, and OH minus would again attack on this acidic hydrogen atom, and we'll be getting something like O minus here and NHPH. Okay, this O minus will then form a double bond with the neighboring carbon atom. Okay, and would be released as a CO2 gas. Okay, we'll get something like this, and this whole would be released as the CO2 molecule. Okay, so in the next step we would be getting something like CO2 would be released, and we'll be getting something like N minus HPH, which again will be acting with water molecule to form something like pH NH2. Okay, hence the final product was formed. So in all the mechanism, in all the steps of the mechanism, how many moles of OH minus were consumed? First, second, third, and finally fourth. Hence the answer was 4. Okay, let's look at another example. We have, you need to compare the rate of Hoffmann bromide reaction in this example. Here we have OCS3 on one place, and we have CS3 on one side with the same amide group. So which would have a better rate of reaction in Hoffmann bromide reaction? So obviously the rate of reaction is dependent on in the RDS. So in the RDS what we saw, that if we have something like this, so this was the RDS step, we have a migratory aptitude on n. This will be breaking up with the n minus and we'll be getting something like, and this will be making a double bond with the carbon atom, so we'll be getting something like this. Okay, so if you look close, this is the RDS step. So based on this only rate of reaction will be determined, because the RDS step only is determining the rate of reaction, and this is the step which requires the maximum activation energy. Hence this determines the rate of reaction from the overall mechanism. Okay, from the various steps of the mechanism, this is the most important step. Okay, so if you look into the formation of this, so what will happen is we have during the migration we need to see the migratory aptitude. Okay, and the migratory aptitude of this is more than the migratory aptitude of this compound. Why? Because this is a plus M effect. It will stabilize more the intermediate 3-member aromatic ring formed during the migration or in the intermediate RDS step, and this is just plus I. Hence, as the migratory aptitude of this is more than the migratory aptitude of the compound on the right hand side, hence the same order can be said for the Hoffmann bromamide reaction as well. Okay, so if you didn't understand how the 3-member intermediate is forming, which is aromatic in nature during the RDS, you can refer to the previous set of organic chemistry lectures, wherein we discussed the concept of migratory aptitude. But still, I will tell you again. So what will happen is, this will take place and this would be a aromatic ring. Okay, aromatic 3-member ring. Okay, so this carbon is getting partially positively charged because of the leaving R minus group. Okay, similarly Br is also leaving, hence this is also facing partial positive group. Okay, so this partial positive would be rotated between the 3 compounds. Okay, and we'll have 2 electron or 2 pi electrons, so it is planar, or we apply the HPCD rule. It is having the Huckel rule of 4n plus 2 pi electrons. It is planar, it is cyclic, it is delocalized, the plus charge is delocalized. Hence the stability of the positively charged 3-member ring matters the most, and in this compound we are having a plus M, which can be utilized in more stability of the 3-member ring. Hence the migratory aptitude of this is more than the migratory aptitude of the phenyl of the toluene group, moving toluene ion. Okay, so with this we come to an end of this lecture. In the next lecture we'll be seeing characteristics of this reaction and some more examples of Hoffmann bromide reaction. So till then, good luck and goodbye.